Hi, I'm Frank.
And I'm Bryson.
This programme's all about the power of electrons and how their discovery led to the invention of television.
Just over 100 years ago, the hunt to answer the question, what is electricity, was being pursued by scientists all over the world. They had discovered that by making very high voltages with the aid of electrostatic generators, they could get sparks to jump several centimetres through the air. That looked impressive, but the presence of air was proving a barrier to their research.
To study sparks jumping from one point to another without air in the way, we need a tube from which the air has been removed. This was extremely difficult 100 years ago because the vacuum pumps they had really weren't very good. With a modern pump like this, it's very easy to remove 90% of the air.
But why get rid of the air? Well, air is a poor conductor of electricity. The electric current has a hard job getting through all the atoms of air that fill the tube. Imagine pushing your way through a dense crowd of football supporters after the match. Halve the number of football supporters, or the atoms of air, and suddenly the journey becomes a lot easier.
Get rid of more and more of the gas, and maybe, if you're lucky, the electricity will be left behind. And that way, you'll be able to see what electricity really consists of. So that's the idea. What Bryson's now going to show us is a demonstration of what happens when you start removing more of the gas from these tubes.
This time I've got another tube which is very similar to the fluorescent tubes we were looking at before. There's no white powder coating inside, so we can see what's happening inside the tube. About 90% of the air has been removed from the tube. And when we produce the spark, I'd like you to notice three things about it. Firstly, the Tesla coil is making sparks of about 30 centimetres in air. But because we've removed most of the air, it's very much easier for the electricity to flow down the tube, and we should be able to make a spark along its full length. Secondly, the spark remains as a very thin pencil-like beam. There's no wire within the tube. It finds its own path and traces it out as a very fine line. And thirdly is the colour of the spark that we see. So Frank, if you can power the machine once more. Now the colour that we produce, that beautiful purpley glow, you may have noticed that it's very similar to the colour of the spark directly in air. That's because that colour is characteristic of air. Some of you may be aware that it's the colour of the aurora borealis, the northern lights, which are generated by electrical charges given off by the sun, spiralling in on the Earth's magnetic field and colliding with the low-pressure gases high in the atmosphere. That purple glow is characteristic of air, but if I take a second tube, which contains a different gas, hopefully you'll be able to see that this time we get the same purple spark from the Tesla to the tube, and then a different colour as the spark passes down this tube. Thank you.
So this is the sort of thing that was the leading edge in the 1890s. It's of course familiar to you today. You all go out, you see the neon strip lights, they're familiar to us. But if you can imagine what it must have been like 100 years ago, when they'd just come out of the era of gas lamps and so forth, and this sort of phenomenon, I mean, this was pretty weird stuff. In fact, in one case, Sir William Crookes, the leading scientist, was so convinced that he was producing ectoplasm in the tubes, you know, the gooey stuff from Ghostbusters, that he became a spiritualist. So, you know, weird things can happen to people when they do leading-edge science.
Today, not only scientists, but the general public can take part in these experiments. A plasma globe with a small version of the Tesla coil can be bought in a shop or experienced at science centres like Techniquest in Cardiff. Touch the globe and tendrils of electrons are attracted to your hands and follow them. Students from Radder School in Cardiff explained it in their own words.
I think there's gas in there because the lines are all wavy like it's going to a gas.
I reckon it could be space inside. Well, not much air for it to move around like that.
There isn't anywhere for the electricity to go, can't escape, so maybe we earth it.
Because it's a vacuum inside, the current's got nowhere to go, so it's using our heat, our hands, the earth source, to go somewhere else.
And the electricity is trying to get out, and when you put your hand on the ball, it flows through the ball, out through your hand and down into the ground.
The purple colour is caused by electrons colliding with atoms of gas. A fast-moving electron collides with another electron circling an atom and sends it off onto a wider orbit. As it falls back, it emits a flash of energy, which we interpret as light.
The electricity is passing through the gas, it's bumping in through the atoms of the gas and shaking the light out of them. As Bryson said, the colour of the light can depend upon the gas that's in there. What we now want to do, though, is to get to the era where the vacuum pumps were getting really good and they could suck nearly all of the gas out of the tubes. And Bryson's now going to show us what happens when you do that.
Thank you. Well, here I've got 3 glass bulbs, which, as Frank said, have had almost all of the air removed. At the centre of each bulb is a small rock or mineral sample. They have little or no colour in themselves, but when I use a smaller version of the Tesla coil, I can produce a stream of electricity from the top that will come down and collide with those samples. Now, where the electricity strikes the rock, it itself will produce light. You may also notice at the bottom that where the electricity strikes the glass, it itself produces colour. So let's just have a look at this first sample. I think you can see that the rock, which before was grey, is now a beautiful yellowy green colour. That's not coming from light outside striking the rock. The light is coming from within the rock itself. The glass at the bottom glows with a pale green glow. Now those colours again are characteristic of the material that struck. In this second bulb I have a different rock sample, but hopefully you'll be able to see the somewhat paler reddy orange glow from this mineral sample. Finally, in the third bulb we have not a piece of rock, but a piece of natural coral. And when I use electricity to excite that, we produce a beautiful blue, purple light from that, with once more the green glow from the glass at the base where that's struck by the electricity.
In the last of those demonstrations, when Bryson shone the electricity onto the coral, you saw the green glow on the glass at the base, but there was a shadow in the middle, the shadow of the coral. And the reason is because the electricity, electrons as we now know, was shining down in straight lines. Where they hit the coral, a shadow was left. At the side of the coral, you see the green glow. So from this demonstration already, you begin to get the idea that electricity consists of something which travels in straight lines. And that is the first thing that enabled Thomson to do the experiment for which we're here tonight to celebrate.
Thomson had made his name studying the conduction of electricity through gases while at Cambridge University. He got the university glassblower to make a special tube for him to his own design. He needed it made to a very high specification so that he could remove all the gas from it. Then he had 2 platinum plates fixed inside so that he could alter the direction of the electron beam that he would pass through it.
The electricity came in at the end here. There's a little metal filament here which would glow hot. Electricity, or electrons we now know, would go shooting along the tube and hit the screen at the front, glass. And when they hit the glass, they made a little green spot, just like the green glow that we saw in Bryson's demonstration a moment ago. But now what Thomson did was he made use of the two forces that Bryson showed us at the start of the talk. First of all, electrostatics. By applying a battery across the little terminal here, there's two little plates inside the tube which get charged up, positive and negative, and he found that the electricity got deflected. It got repelled away from the negative plate. The green spot moved. Then what he did, he put a coil around the outside of the tube to make a magnetic force, and that also deflected the beam. Fine. But then he did the really neat thing. He used both the electrostatic and the magnetic forces and balanced them in such a way that the green spot didn't move at all. Now, why on earth should he do that?
By balancing the two forces, Thomson was able to measure the particles that made up the beam of electricity. And he found to his amazement that they were 2,000 times lighter than the lightest particle then known, the hydrogen atom. These minuscule particles are what we now know as electrons.
It was at this moment that he realized that electrons, as we now call them, the carriers of electricity, are smaller than atoms. They're inside atoms. They are fundamental constituents of everything. You, me, the whole universe. And that was the moment of discovery for that.
Well, it's said that when Thomson was performing these experiments, he spent hours, days, weeks of time staring at the end of the tube, completely to the exclusion of family and friends. And I think it's quite ironic that today, around the world, millions of people spend hours, days, weeks staring at the end of Thomson's tube to the exclusion of their family and friends, because one of the simplest developments from Thomson's tube is in fact the modern television set. Imagine how we would make a tube today. We'd take a glass bulb, strong enough such that when we pump all the air out it doesn't collapse, and then to improve its brightness we'd take one of these mineral samples, let's say the yellow one that we looked at first, grind it up into a fine powder, mix it with a little bit of glue, and smear it on the inside front of the bulb.
In this case, the phosphor is painted onto silver paper and a bell jar is placed over the top. All the air is pumped out and a stream of electrons are fired at the phosphor. Like the minerals in the other jars, the phosphor gives out a glow.
Now we can use magnetic coils around the tube to move the beam from side to side. And so we can produce a spot that moves across the screen. Now the brightness of that spot can be varied. We simply control how much electricity is flowing in the beam. The more current, the brighter the spot. Less current, the dimmer. And that spot can be made to travel faster and faster. In fact, we can make it travel at over 10 kilometers per second. And when we do that, we don't see a spot, but we see a solid line. Now, we see a line because of the way our eyes work, and because samples such as this don't give out their light immediately, but take a short period of time to give it out after the beam has struck. So we can produce a line. We can then introduce a second set of coils and move that line from the top of the screen to the bottom. And again, we can make that line move slowly, or faster and faster and faster, till eventually when we move it fast enough, we don't see a line, but a solid picture.
The picture on a modern colour television is made up from those three colours, red, blue and green. The long cathode ray tube is what takes up all the space in the back of the television, and at the back of that is the electron gun.
This is the gun section of the tube, which is inside the neck here. The beams are emitted from the cathodes at the back, 3 beams, which pass through 3 apertures, 3 individual electronic beams. Their purpose is to land on 3 individual phosphors, excite them and produce red, green and blue colours, which mixed together will give you a white colour. which then passes down the tube, is bent by the coils and the magnets to align on the 3 phosphor slots on the front of the tube. If I put this magnifying glass to the front of the screen, you can see quite clearly the 3 different coloured slots, red, green and blue.
Although the technology is almost 100 years old, it still accounts for 99% of TVs sold. That could be about to change.
For years, people have been talking about the possibility of flat-screen televisions. You could wear them on your wrist, hang them on the wall. Well, maybe this is it. We're in Cambridge to look at the latest technology that might well replace the cathode ray tube.
Still under research, this tiny television screen represents a leap into a new technology that many scientists pooh-poohed: light-emitting plastics. The inventor and leader of the research team is Jeremy Burrows.
In the cathode ray tube, you have an electron source and fire the electrons to your target, which is your phosphor, and therefore you need the electron source a long way away from the screen if you want a large area screen. With this system, what we have is the electrode right actually on the polymer itself, and we inject the electrons into the polymer, and it therefore gives that light. Therefore it can be very, very thin.
The base is coated with a thin film of plastic, which can be energized by electrons passing through it. Dots of blue, green and red will be applied through a printing system, but getting the colours right isn't easy.
It's an ongoing process. I don't see any particular difficulties in getting the right colours. What we have here is an example of 3 of the colours that we can have developed. There's the blue and the green and the red-orange here. Well, blue has been the hardest colour to achieve, and we spent most of our effort over the last 9 months on that.
The first practical use of the television will be as the display screen on a mobile telephone. Although still very small, the developers claim that one day they'll be able to make screens 2 meters wide. It'll be viewable from any angle without distortion, and it'll be very economical to run. At the end of the day, you can fold it up and put it away.
I think it'll be in games like Game Boy, mobile telephones, in your home, hanging on the wall instead of having a large television which takes up a lot of space. It can literally just hang on the wall. In fact, we expect the thickest element of the screen to be the electrical cable coming into the screen rather than the actual screen itself. My idea would be so that you can just hide it behind a picture, because I hate to see technology in the home.
You're still not impressed? Well, electrons can do much more than just show TV pictures. Watch the last program in this series and we'll see how electrons are creating echoes of the Big Bang and revealing how the universe came into being.